Hello everyone. In the previous session, I have clearly explained the concept of a cantor ternary set. Fine. Anyhow, I am revising the concept once again. A cantor ternary set is none other than when you are going to divide an interval, a closed interval say 0, 1 into 3 equal section in such a way that they should not include 1 in between the fractional number. Fine. So that is what the meaning of cantor ternary set. Or else I can say cantor ternary set as intersection of all CNs. Fine. That is closed interval. So clearly length of each interval, when you're going to divide an interval 0, 1 into 3 parts, you will get at each stage you are going to get 2 closed interval. You just go through the video once again so that you will clearly understand. And moreover, I have told you something like each length of each of the interval will be clearly equal to, or length of an interval of a cantor ternary set is 1 by 3. For C2 it is 1 by 3 square. So when you continue the same procedure, the length will be 1 by 3 power of n. Remember, in a cantor ternary set, the length of each interval is 2 power of n. Each number of intervals is 2 power of n. In the sense, in the first interval, for the first cantor ternary set, you will get 2 closed interval. In the second cantor ternary set, you will get 4 closed interval. It is clearly explained in the previous video. You can go through that. So you will get 2 square in C2. Fine. So in general, how many intervals you are going to get? 2 power of n intervals. So remember, in a cantor ternary set, for 2 power of n intervals, which is of length, each of length 1 by 3 power of n. Fine. Now, and we have already proved in the previous session that you have an unique expression for a cantor ternary number, that is an by 3 power of n. So I can represent any element inside the cantor ternary set as an by 3 power of n, or it is a representation used for decimal number. Fine. Now we have certain theorems based on a cantor ternary set. In this session, let me continue with the theorems. First theorem is that it is important theorem. Statement is something like we have to prove a cantor ternary set. This is what the cantor ternary set is. C is equal to intersection of n is equal to 1 to infinity. Cn is uncountable. It is one of the property of a cantor ternary set. And the proof is exactly similar to the proof of proving a real number R is uncountable. You have already done this in real analysis. Hope so you remember this. R is uncountable set. It is one of the example for uncountable set. You have already done this proof in real analysis. So same methodology will be used here also. So what we have to prove is C is uncountable. Now I am going to prove this by contradiction method. In the sense, let me assume C is countable. Fine. C is countable. In the previous session I have told you, if you are going to write any number in a cantor ternary set, it will be of the form fractions. Decimal numbers. Like either it should start with 0 or it should start with 2. That is what the ternary system is. Why? Because as I already said, ternary represents integers 0, 1, 2. As we remove middle part in each session, so you are going to get either 0 or 2. So an will be always equal to 0 and 2. It is already clearly explained in previous video. Fine. Now what I have assumed is C is countable, but what I have to prove is C is uncountable. Fine. Now let me take C1 as an element something like 0.A11, A12, A13. The proof is just a logic. The thing is you have to understand. So let me take C2 as A21, A22, A23 and so on. Similarly C3 as 0.A31, A32, A33 and so on. So as per the definition, C will be our cantor ternary set. It is the intersection of all the CNs. So this is what the CNs is. Now in this C1 to C3, we don't have any number which contains 1. Fine. That is what the definition of cantor ternary set. So in a cantor ternary set, there will not be any number which contains 1. In the sense, either it should contain 0 or it should contain 2. As we eliminate 1 in each session, so you are not going to get 1 here. Fine. Now what I am going to do is, so let me write the statement in order to understand. Cij is ternary numbers. Obviously when I said ternary set, it is a I'm sorry, when I said cantor set, it should include ternary expression. So ternary set without using digit 1. So I'm not going to use the digit 1 here in any of this cantor ternary set. Now let me assume one of the decimal number, say, which is of the form 0. So when I said decimal, it should be 0.B11, B12, B13, so on, and in such a way that it takes the value 0 if ANN is equal to 2, and it takes the value 2 if ANN is equal to 0. Meaning is that the diagonal element in the cantor ternary set, that is A11, A22, A33. This is what the meaning of ANN is. So if this number is what we say ANN is none other than A11. If A11 is 2, B takes the value 0. Similarly, if A11 is 0, then B takes the value 2. I'll give you simple example so that you understand very well. Suppose let me consider a set C as, say, 0.2, 0.02 and so on. Fine. Now, as per the definition of B that I have assumed, what it says, as per the definition of B, it takes the value 0 when ANN is equal to 2. ANN in the sense, this element is A11, this element is A12. Fine. So A11 I have to look for. Why? Because this is 2. Fine. So, or else I can give you one more simple example. C is equal to 0.2, say 22020. Fine. Now, if it repeats again and again, in the sense it will not terminate. Again 2020, it will continue as it is. Now, as per the definition of B, you have to look for A11 position. A11 in the sense first element. So, first element is 2. So ANN is 2. So if ANN is equal to 2, I have to replace B as 0. Clear? Now look at the second element. It is A12. So I cannot change this. Now I have to go through the second set in the same manner. Suppose if it has say 0.022. So in the second position, if it has 0, B takes the value 2. So this is what the meaning is. In the sense, if A11 is equal to 2, I have to replace B with 0. If A11 is equal to 0, I have to replace B with 2. Fine. Now, if you are going to do the same procedure, the decimal point B or a point B will be containing the digits only 0 and 2. But not other than 0 and 2. Or else I can say it will not contain 1. For example, suppose if C is equal to 0.2 and 0.20. Fine. Now decimal point B will become like I have to change A11 position in the first element. So 0.0. Again it is A12. So I cannot change anything else here. Fine. In the sense, suppose if I have one more element, say 0. Here in this element, in this position, it is A12. In this particular number, this position is A11. This position is A12. So I cannot change A12 here. I will change just A11. Now, next look for the second element. Here in this case, A11, A12. Again I have to change A11 position. A12 remains as it is. So again the same procedure. A11, A12. I have to change A11 since I have 0. As per the definition of B, when I have 0, I have to put B as 2. Clear? So you can clearly note that this number is entirely, or I can say this set is entirely different from this set. Meaning is that whatever the element you have in a cantor ternary set C, you can form an infinite number of sequence B. I'm repeating once again. I have assumed a cantor ternary set in such a way that it contains the decimal number. Fine. Now it should not contain 1 as per the definition. Why? Because it is a cantor ternary set. 1 will not be there as we remove middle portion. Now what I did is I have assumed the number B in such a way that I have defined this as 0 when diagonal element is 2, and it takes the values 2 when diagonal element is 0. This method of proof is similar to proving R is uncountable set. It is clearly explained in the real analysis. Please go through that. So this is what I have defined. Now if you are going to use this procedure in the assumed number b, you will get set of numbers which will repeat one again and again. In the sense, you will get an infinite sequence of number. So for each number assumed in the cantor ternary set, we will get an infinite sequence of numbers of b. Fine. So I'm telling about sequence B, which is subset of C, right? It will be definitely in C. Why? Because C is also containing a number other than 1. In the sense 0 and 2, it contains only 0 and 2. Similarly, I have obtained an expression B which contains only zeros and 2s. Why? And moreover, B is subset of C. B is infinite here. Why? Because this process goes on repeating, so we cannot count the number there. So B is infinite. B is subset of C, but what we assumed is C is countable. It cannot be possible, right? So it is contradiction to our assumption. Therefore, C should be uncountable. Oral theorem. I'm just repeating once again. I have assumed the cantor ternary set with elements containing decimal numbers. So as I said, cantor set represents a ternary numbers. In the sense, it contains 0, 1, 2. We are going to remove 1 so that it should take values either 0 or 2. Fine, that is what I have written. Now, I have defined a sequence B in such a way that it is a part of a cantor ternary set. Moreover, it takes the values, diagonal element value as 0 when it is equal to 2 and 2 when it is equal to 0. So when I do that, you can note that clearly a set B is infinite number of sequence. In the sense, the same values goes on repeating. It contains infinite number of elements. But what I have taken is B is subset of C. So it cannot be possible. B is infinite set, but what I have assumed, infinite is none other than we cannot count the element in set B. But what I have assumed is C is countable. So it cannot be possible. Fine. So we arrived at contradiction. C cannot be countable. Therefore, C should be uncountable set. Hope it is clear. And the second theorem based on cantor set is a measure of C is 0. That is m star z is equal to 0. And I'm sorry, I forgot to explain while doing outer measure. Remember, outer measure is same as Lebesgue outer measure. Full name of outer measure is Lebesgue outer measure. So they can ask Lebesgue outer measure of C is 0. C is cantor ternary set. So cantor set is 0. Measure of cantor set, we have to prove it is 0. So as I already told you, so C can be written as intersection of all Cn's. Fine. Now Cn is none other than it contains union of all the intervals. As I already told you, it contains 2 power of n number of intervals with length 1 by 3. So I will write the same 2 power of n sub-intervals of length 1 by 3 power of n. For all n numbers, you will get 2 power of n sub-intervals of length 1 by 3 power of n. So I can write this as Cn is equal to union of all those intervals. Now what I am going to do is, let me take measure on both sides. So when I apply measure on both sides, you will get m star Cn is equal to m star union of 2 power of n subintervals of 1 by 3 power of n. If I have 1, I am going to do 1 into 1 by 3 power of n. Since I have 2 power of n, 2 power of n into 1 by 3 power of n. This is number of intervals, this is length of each interval. Fine. So m star of Cn, I am using monotonic property here. So when you use monotonic property, union replaced with summation, and obviously it will be subset. So I can write less than or equal to summation 2 power over in all the intervals is number of intervals I have to take here. So 2 power of n intervals. I am taking summation over all the intervals. M star 2 power of n into 1 by 3 power of n. Fine. And we have proved this expression in one of the theorem. Like when you have measure of union, if you take that measure inside, the equal sign will changes to less than or equal to, and measure should take inside the summation symbol. Something like I have proved this theorem already, so you go through that theorem. Like m star of A, if I have, which is the, or else I have equals or subset, whatever may be the thing, union of some, like m star of union of some value, whatever may be the value, like 2 power of n. If you are going to take the measure inside, that will become like less than or equal to, since you have to take measure inside, union will become summation, so m star of 2n. I have proved this theorem. If you want, I can state the theorem, and the statement is something like if for any open set A, summation m star of union n is equal to 1 to infinity, an is less than or equal to summation n is equal to 1 to infinity m star of an. I have proved this important theorem, and the same concept I have applied here. See here, here I have length of all the open intervals, so I am applying measure, so equal sign is become less than or equal to, and I have to change union by summation symbol taking over all the subintervals, that is 2 power of n interval. So I can write m star of cn is less than or equal to measure of a number it is, so I can directly write this as 2 power of n by 3 power of n, or else I can write m star of cn is less than or equal to 2 by 3 whole power of n. And remember, as n tending to infinity, or else I can say for larger values of n, for larger values of n, 2 by 3 power of n will be equal to 0. For larger value, when value of n increasing, 2 by 3 will value approaches to 0. So this value will become 0. Meaning is m star of cn is less than or equal to 0. But what we have to prove is m star of c is equal to 0. Remember, c is different from cn. C is intersection of all the cn's. But what we have proved is m star of cn is less than or equal to 0. We know that c is subset of cn. Right? Why? Because when you C is the largest set, Cn is, when you are going to combine all the Cn's, you are going to get C. So I can write C is subset of Cn, or else C is contained in Cn. Fine. Now for each values of n, I can write for all n. Now let me apply measure on both sides. So I'm going to get m star of C is subset of m star of Cn. Now what I have proved is m star of Cn will be less than or equal to 0. So I can replace this subset by less than or equal to 0. M star of C is less than or equal to 0. Now for the reverse inequality, it is obvious by the second property of Lebesgue outer measure, measure of any set is positive, right? Or else I can say m star of C is greater than or equal to 0 by the property of Lebesgue measure. Now from these two expression, I can say m star of C is equal to 0. Fine. I am proving measure of cantor ternary set is 0. This is by the definition of cantor ternary set, Cn. Fine. It is the union of 2 power of n subintervals of length 1 by 3. In each cantor ternary set, you will get 2 closed intervals. Fine. So in general for n, it is 2 power of n. It is clearly explained in the previous video. And each of length will be 1 by 3 power of n. I have applied measure on both sides. So again applying the theorem, you will get this. Since measure of a number is again a measure, that number itself, so I have written the same number. For larger values of n, this value will be equal to 0. So I have written the same here. Now by the definition, C is subset of Cn. Why? Because C, all the C's will be contained in Cn also. So let me apply measure on both sides. So if you do that, measure of Cn is always less than or equal to 0. I have proved this. So that is what I have replaced here. Now as per the property of Lebesgue measure, outer measure, measure of any set is positive, that is m star is greater than or equal to 0. By combining these two expressions, I have obtained m star C is equal to 0. That is measure of a counter ternary set is equal to 0. And the next very important concept is G sigma and, or else I can say G delta. You remember this symbol as G delta and F sigma sets. It is important. It is asked in the year 2016. And 2018 as well. Fine. Now let me explain first concept, G sigma set. G sigma set in the sense, suppose if you have any open set, say Gi. Fine. If you have open sets Gi. Gi in the sense it contains I number of open sets like G1, G2, G3, G4, so on. So it contains infinite number of open sets. If Gi is collection of all the open sets, and if you are going to take intersection over all the open intervals, we say that set as G delta set. I am repeating once again. G delta set is none other than a countable intersection of open sets. GI is a collection of open sets. So if you take intersection over all the open sets, you will get G delta set. So G delta is a countable intersection of all the open sets. Open sets. Clear? Now second concept is F sigma set. It is just opposite to, or else I can say it is complement to G delta set. G delta set and F sigma set are complement to each other. F sigma set is none other than, suppose if Fi is a closed set. Fi is closed set, in the sense it contains n number of or infinite number of closed sets, and if you are going to take union over all the closed set, we say that as F sigma set. Difference is that here you are going to consider open sets intersection. In F sigma set, we are going to consider union of all the closed set. G delta set is intersection of all the open sets. F sigma set is union of all closed set. Clear? Now we can have a combination of G delta and F sigma set. Have a look at that. First one is, I can say F sigma delta set. F sigma delta set. Fine. Now F sigma is none other than, it is union. When I said sigma, it is union of closed set. Clear? So first you have to write F sigma, union of all the closed set. I is equal to 1 to infinity. Clear? Now what we have is delta. Delta in the sense you have to put only intersection. That's all. Remember, F sigma delta in the sense, first you have to take union of all the closed set, then you have to put intersection for it. Then the obtained set is called as F sigma delta set. Clear? Similarly, we can form G delta sigma set. G delta sigma set. Similarly, first you have to write G delta. As the definition says, G delta is intersection of all the open set. So first you have to take intersection of all the open sets, followed by sigma is none other than union. You have to put only union for that. So the resulting set is called as G delta sigma set. Clear? Now we have an example for this. Remember, every open set in R. So when I said R, it is a set of real numbers. So every open set in a real number is G delta set. Open set in R is G delta set. It is just a one of the example, or else I can say properties also. And every closed set in R is one of the example for F sigma set. Every open set in R is G delta set. Every closed set in R is F sigma set. Clear? Now let me tell you some of the properties, or I can say examples of. Instead of saying examples, it is better to say properties, and you need to remember these properties. So just now I have told you, first property is that every open set in R is delta set. Every closed set in R is F sigma set. As I said, it is intersection of open set. So in R, if you are going to consider any open set, it will be G delta set. Similarly, in R, if you are going to consider closed set, it will be F sigma set. Clear? And third property is that every open interval in R. So if you are going to consider a real number, and if you are going to consider any open set, that will, any open interval. I'm talking about open interval. That will be an example for F sigma set. Clear? Why? Because we can form a closed interval, and within the closed interval we can form an open interval, as we already derived that open interval as union of all the closed interval a plus 1 by n. Using the derived theorem, we can say this. Fine. So remember, any open set, or I can say any open interval in R is F sigma set. Clear? Similarly, open set is also fourth one. Open set in R is also F sigma set. So summary is that in real number, if you are going to take any open set, if you are going to take any open interval, everything will comes under F sigma set. Also, a closed set if you're going to, closed interval. Why? Because we can find open interval inside the closed interval. Closed intervals is also an example for F sigma set. Clear? So as I already said, every open set is F sigma set, right? So if you're going to consider any open set, say O, we can express this as per the property 1, I is equal to 1 to infinity, union of all the open intervals. So remember, union of all the open intervals will be F sigma set. Why? Because I have already told you, In, if you are going to consider any interval, open interval, that will be an example for F sigma set. So when you are going to express O as union of all the open interval, again it will be F sigma set. Clear? Now coming to the property of G sigma sets, one of the properties is that if you are going to consider any real number R, then any closed interval inside R will be an example for G delta set. In the sense, if you are going to consider a closed interval AB, that is intersection of A minus 1 by n, B plus 1 by n. Remember, if you are going to talk about F sigma, if you are going to talk about F sigma, closed interval AB can be expressed as union n is equal to 1 to infinity A plus 1 by n, B minus 1 by n. Clear? When you talk about F sigma set, if you are going to take closed interval as F sigma set, you have to take union, and first term will be plus, last term will be, n term will be minus. Similarly, if you talk about G delta set, when you are going to consider closed interval, it is an intersection and first term with negative and second term followed by positive sign. And next point is that every closed set in R is G delta set. As I already said, whatever the closed set you are going to take inside R, that will be an example for G delta set. And remember, G delta set and F sigma set are complement to each other. Why? Because one is open, another is closed. So I can say complement to each other. So these are the properties of F sigma and G delta set. So hope it is clear. Continue in the next session. Notes will be forwarded in the group. Thank you.